All right. Looks like we are in business. Okay, now it looks like we're in business. Looks like there's a little bit of delay, but we have a good stream health. So, welcome. Um, so, what I'm going to be doing today is I've been getting some feedback of, these ADTs are great and all. But, hey, Bob, how are you doing? Oh, that's weird. It says here, hold on, let me refresh this. Oh, interesting. So it says that I have no one watching, so I think these numbers have been lying to me for a while. Huh. Well, anyway, welcome. How are you doing today, Bob? Is it all right if I call you Bob? Um, so to back up a little bit, we have I've been getting a lot of feedback and things like that through private channels that these ADTs are really good and all, but a lot of people are just starting fresh. Like they see the how would you say, like the things that I'm doing, like setting up a state and things like that, and don't really grasp like the composition and currying stuff that's going on in there. So I figured, in light of my theory series that I'm about to start releasing episodes for, it might be nice to parallel that with a more of a practical. So that way you can kind of see like how you would use currying, composition, or all these cool functional techniques, the stuff we're going to learn about in the theory, and see like what that means practically. We'll have some practical stuff in there, but it's not really as practical as these sessions are going to be. So we're going to start off, we're basically just going to go through, we're going to start with composition, currying, partial application, that sort of stuff. And then next week, we're going to move on to combinators and combinatory logic and kind of go through how those are used. And then we'll move on to like predicates and predicate handling. And along the way, I'll contrast differences between Crocs or Ramda. So if you're more of a Ramda user, you'll be able to see like what these types of things would look like in Ramda versus what they would look like in Crocs. Because we have a lot of the similar functions, just some tiny little tweaks and differences to them. So it's good to kind of show those. So like I said, this is going to be more of a beginner episode. But I wouldn't really say beginner, more of a back to basics episode. And mostly it's just to contrast, get kind of everyone up to speed. And yeah, another note. So next week as well, I talked with my boss about it today. Another thing I've been getting is a lot of the people that seem to follow me on the tweeters and all of the little channels and Getter and the places I go, a lot of them are in Europe. So much so, and I get more disappointment or people saying, oh man, it's 4 a.m. or it's, 3 a.m. here whenever you're doing this. And I really had some questions and things like that. And I'm getting a lot more of those responses than the people that are showing up for the live codes and participating. So I talked with my boss today, and I knew he was going to say it was all right. But so basically I asked them like what I was going to do. And they said, or he said it was fine for me to take like an hour and a half off work Tuesdays at 9 o'clock my time. So that's going to put the live code session at, I think, around 5 in Great Britain, 6 in Central, and 7 or 8, like, as you go further, I think. My time zones aren't very good. But it'll be more in line with European times. And it's also really good because it puts it at lunchtime for the East Coast people. So people that might be on lunch break or something that want to jump in, it will still cover some of the Americas as well. So I'm going to try that for a while, and hopefully, I'll be able to appease some people. Now, there are going to be times where I'll switch to the evening, like when I'm on call. Certain weeks I'll be on call, and it seems kind of weird to put that burden on my teammates because, of course, someone would cover me, but I don't want to ask people to cover me all the time because that's just silly. So, yeah. Anyway. If you have any thoughts or anything about that, please let me know. I'm always around in the getters. You can hit me up on Twitter. I'm EvilSoft on Twitter. EvilSoft in most places. But yeah, so with that, we kind of got the business and housekeeping out of the way. Let's get into it. So what we're going to cover today, we're going to start off talking about composition. And functional composition. And I'm going to try to give some examples of what it looks like imperatively. From Australia here. Yeah, I know. I have a couple Aussies and Kiwi friends too. So, and that's why I think depending on how the viewership, good call, Bob. Depending on like the viewership, I might be able to switch, like maybe every other week or something, do it to where it covers like the people in the West Coast and up to late in the evening on the East Coast in America, and then get like the midday people for all my Kiwi and Aussie friends. Or I don't want to say friends, that's a little presumptuous of me. The Kiwi and Aussie people that are interested. I like to think everyone's a friend. Anyway, it just makes life really good. Okay, so yeah, I'm going to try to accommodate, but it's really hard, and I want to give everyone to participate. So we'll just see like where the numbers fall out and things like that. And also, I am totally up for disruption. So if you do have any questions or anything, go ahead and throw stuff in the chat. I constantly monitor that. So anyway, let's get started. So what we're going to do is I'm going to present some examples. Now I went ahead and through the voodoo of copy paste magic, I created a couple things just to get us started, right? Just a couple functions so we can kind of see cases for when we would want to do composition or things like that. So here we have this, really imperative flow. Now, of course, we could go ahead and do something like this, where we take this to that, and then df this to that, and, replace this out here. But it's very hard to come up with an example that doesn't hide details. So what I'm going to do is kind of create, this is kind of a, how would you say, a contrived example, but I want to give you something to look for, right? So a lot of times you'll want to use composition, or you'll start noticing things about some of the functions that you write whenever you start creating state, right? Like we could have written this another way to where we weren't creating state, but I kind of wanted to demonstrate it as a way to kind of send off a red flag that, hey, you know what, maybe I should do composition here or something along those lines. So even though this could be to where we're not using state, we're not creating this sum variable and doing things, I'm just doing this to kind of demonstrate like what the signs or the red, not really red flags, but signs that you could utilize composition here. So, and like I was saying, usually this happens here whenever you have some sort of variable that you're calculating, right? This right here is a two-step process. We're taking in two numbers, we're adding those numbers, and then we're going to sum those numbers. So we're basically just getting an average over here. So let's just go to here, and we'll do math, and we'll give it the numbers 4 and 5. So we see that the average of 4 and 5 is 4.5. So like I said, we have two things that are going on here. So we can create a function, and we'll just call this add, right? And typically, whenever you're building or using composition, you're going to want to take these steps where you have assignment and, how would you say, return the assignment as the result. So basically, we have two steps here. So this could be two functions. We're taking two numbers and adding them. And then we're going to take those two numbers and then divide it by 2. So we can break this off into a two-step process to where we just take an A and a B, right? And then from there we return, and let's just do this. We'll say an A plus B, right? So that captures the first one. So here we can just do this, and we'll say that sum is, we'll do add A and B. So now we have this, but we actually are, we have this other thing going on here called have, or we're basically going to have this after we have the sum, right? Because we just have 2. It looks like an average, but really it's taking in 2 numbers and getting the half of their sum. So here we'll just create a function called have. And half is just going to take any x, and we could put some safety around this, you know, to make sure, you know, we're dividing by a number, things like that. But we're not going to concern ourselves with that at this point because we didn't concern ourselves with the other bit. And all half does is it takes this and divides by 2. So see how we do this operation, we divide by 2. We could then change math up here to actually do something like this. And we've captured both of our actions inside of 2 separate functions. This takes in 2 numbers and gives back a number. And then this takes in a number and then returns another number. So what we did was we took the result of this and we added it, or we took the result of that and put it in as the input to this. So that's how we broke out down these 2 actions and to make them 2 different functions. So to make this a little clearer, let's do some of this, some of that, and then let's just move these up to the top because we would probably want these defined beforehand, and we still get the same result. Now this right here, and you'll run into this all the time. Think of all the times that like you have an object and you want to pull something off the object before you send it to another function to operate on it. You'll run into this, and I'm sure if you look through your code, you'll run into functions where the result of another function becomes the input of another. And this is what a function composition is. And as a matter of fact, if we look here, we can make a real simple helper that takes a function f and a function g. Oops. And then returns a new function that takes an x, and then all it does is it takes f and g and then applies x to that. So that's all a composition is. So now, instead of doing this, and to get this to work with our flow, we're going to have to do something a little more. We're going to have to do args here. And the reason why is because the input to add actually takes 2 things. So here we can just go in and do another spread, and we'll call it args. And throw that there, and throw that there. So now all we need to do to get math is create this compose helper, or use this compose helper. So here all we do is go in and do compose. And we just do half because half has to be half. Hello, Ronaldo. Dominican Republic. That's awesome. I've never been there. Well, there's actually, I don't know why I said that. There's a lot of places I haven't been. But, all right. So there. Now we're all good. So now we could just take this half, and then we take add. And one of the things you'll notice is the way that this compose, well, just to make sure this still works, we give it a save and we see that we got back 4.5. So we captured that pattern of taking one function and calling it with another function like we have here. See? And we squirreled that pattern away into this one helper function that will take care of that for us. And this is what you would use composition for. We basically take that one function that we had, and let's go ahead and just paste that in again just so we can see it. We take that one function that we had that was a 2-step process, and then we broke it up into another, or into these 2 functions because each one is a certain step in this computation. And then we just applied the result to it. We composed them together. We took the result of the sum and then sent that off to the half, which then divided it by 2. right? Does that make sense? But now, since we have this pattern together, or working in this way, one of the things to notice, sorry, I totally went off script here. I had an idea how I was going to present this, and now I am at the point where I am totally off script. All right. So what we want to do here, or what this is basically trying to show, is anytime we have any type of step, or whenever we're creating state or anything like that inside of one of our imperative functions, we can always break this off into other functions. Because what if there's a place that we want to do this addition again, and we want to take two numbers and add them together? We would have to write this A plus B code. And right now we're not doing any checks, but maybe we want to check to see if these are actually numbers, so we don't actually send strings in. Because look what happens here, you know, because it's good old JavaScript. Let's actually df to this. Oops. Let's do a df to this. And then we'll do add. And we'll say, hello, unicorn. Right? So now we get hello, unicorn. Because this is a completely valid operation. So maybe we want to put something in that always checks to see that these are numbers, right? So what we would have to do at some other time, or in any time that we wanted to add these two numbers together, we would have to put in a check to make sure there's numbers or things like that. If we were just going to do the real simple calculation of taking two things and dividing them by 2, right? So another thing to notice about this, let's put this back and we get back to 4.5, is notice how whenever we first had this defined, it was half and add, and then the actual value, right? So 3 and 4 or whatever. Notice that the order of these functions are actually the order of how we would write it naturally, right? So we compose things, it goes from a right to left order. You'll see a lot of people use pipe or things like that, and that's totally valid, and there's a lot of times I use pipe. But when you use the compose operator, and pipe is basically just the reverse of this. So if I were to flip these two arguments or do whatever, it would actually take care of that for me. It would, how would you say, compose it in the opposite order to where, like, say this was pipe. And actually, we'll show that a little later. No, we'll show that a little later. But it would basically be flipped around. So the add would be here and the half would be here. But if you look at the way this is, we define it to the left and the data moves in a right to left fashion. So we actually apply these attributes, or we apply these parameters to it over here on the right, and then it moves to the left all the way to our assignment or to the result that it's spitting out. So a lot of people have a hard time reading compositions when they're getting used to them, but really I think it's because it's of a new context, because this is how data flows. You define something out to the left, and then the data comes in on the right and then flows to the left. But we're used to like doing this function thing, right? To where we go from a top-down function. So we might have f, and then when our parameters come in and we work down. But when you're working in this sort of style, the result's going to come in here. Like if I were going to apply numbers to this, I could just do, 4 and 6 or whatever, and then just do math. Notice how the data comes in on the left or on the right and then moves to the left. So that's a good way to kind of train your mind. Now, a lot of times I'll use the reverse of this, which is pipe, whenever I have, like when you have a bunch of promises in something. So like you get your input and then you do a promise to go to the database. So you'll have these dot then, dot then, dot then, dot then. Whenever I have a lot of cases like that, or I'm doing a composition where it's more of a data flow, at that point in time, and I picked this up from a bunch of the people at work, they do that a lot, and it just makes sense in that aspect. just because we're so used to doing the promises that way. A lot of times pipe is used for that, and I'll use pipe for a top-down flow. But typically when I'm just building out these compositions or these really simple compositions, I'll always use compose whenever it's like one or two things or two or three things. I'll typically just use compose. It just seems to read better, things like that. But some people really enjoy using the pipe and things like that, and there's nothing wrong with that. It's just you should get used to reading them both, and you can provide context for each one of those functions. So like if you know, hey, I only use pipe for this fluent style or this top-down flow, then you know that you have a top-down flow, if that makes sense, right? So you're able to actually communicate to your teammates and other things saying that this is a data flow. So pipe is very useful. Now, this is such a common thing, like that's pretty much most of functional programming, that Ramda actually provides one. So we'll do require and Ramda. And it's just called compose. So here if we do our compose, oops. See how we still get back the 4.5? And that takes care of it. Notice how over on the right, we didn't have to like spread the args. And it just took the args that came to this and then applied them to the first operator. So it takes care of that little arg spread that I was doing. Also, if we look at Crocs, Crocs also has one. So we'll do compose, and this will be Crocs. Crocs also has a compose operator. We'll call that compose, and it does the same thing with the spread. One of the things you have to be careful, though, I guess we don't have to worry about that yet because we are going to deal with that when we talk about currying. So never mind, I totally jumped ahead of myself. All right, so this is just the basics of composition. If you want to see also, Ramda has a pipe operator. So we can do r.pipe. And it does the same thing. But notice how we reversed it. So now it's basically the result's going to come, and see how this is awkward? The result comes into the top of this function and moves out to the right, even though assignment and everything else is over on the left. And that's what I mean. Even though pipe kind of makes sense, it's really awkward when you start thinking about how these functions go together. So I would recommend getting used to compose in cases where it makes sense, but you don't have to use it. And also we have a pipe, actually let's keep this compose. We have a pipe also available inside of Crocs that does the same thing. See, and you get the 4.5. So at this point, Ramda and Crocs, the way that they do their compose function, pretty much dead on, same sort of thing. There's no difference there. So now we'll talk a little bit more about compose. One of the neat things, or one thing about compose, is say we have this other function here called add label. So say we want to take this and we want to add a label to this. So we want to take some sort of number, and then we're going to take that number and then make it into a string. And that string will have, average score, blah, 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 and then have it be a number itself. So this is wrong. This is add. Is that right? Perfect. All right. So now we have this whole other thing that we want to do. So we want to take the result from this math and actually add a label to it that says average score. So one of the things we can do is let's go ahead and put add label here. Oops. And we see that now it took that half and then put it into this next function. So we're able to take the result of this function and pass it into here. Now, a really neat thing about doing this or working with compositions like this is they are what's called associative. So what that means is we can kind of move these around because kind of under the hood right here, we're taking these two functions and composing them with this function. But we can actually, the same thing that we're doing here can be represented like this. See how we get back the same thing? And all we really did was we moved around or we added some parentheses to it. But because it's associative, we didn't have to do that. We could do this. And this is the exact same thing. See how we can take compositions of other compositions and then insert them in? So here, we can create a function, or we can go back to having a function called math, which is basically just the composition here. And we can create another one called math label that is just another composition of of math and add label. And let's clean this up a little bit. And now all we do is call math label. And we still get back the average score. So that's the really neat thing about these compositions is as long as everything happens in the same order, it doesn't matter. Like say we have a functions f, g, and h. It doesn't matter if we compose f and g first and then apply h, or if we do this. We can move these parentheses around and they're exactly the same thing. And that's because of the associativity property of a composition. Now, later on, once we start talking about functors and all kinds of other neat things, we'll see that this is a very important property, and it actually helps define like the structure in a given category. Right now, it's not so important to worry about these sort of things, but it is good to know from a practical point of view that I can extend and make other functions, and it doesn't matter as long as I keep the order of these the same. It doesn't matter how I group the compositions. And it allows you to, capture reusable functions and things like that in a manner that they can be reused and be more general in other places. So for instance, this G after H could be something that's very, very general that works in many cases, but we can just go ahead and then compose this F after it, and then we'll get back something that's context specific for it. So anyway, that's some neat things to understand about composition. And because really pipe is just a flipped composition, you get the same thing. So there's really no reason to go on and on about that. So now we have these reusable functions. And let's see here. Okay. Yep. So that's the average score. Oh, that's what I did wrong. Ha! So this is kind of I don't really know what else to say about composition other than you can take very large and crazy, as we'll see in a little bit, imperative functions and break them up into reusable steps. And then by using composition, all it is kind of like taking different Legos, different like blocks, and kind of sticking them together, right? And getting these real general functions to be used in a manner that applies to the context that you're doing. And speaking of context, that's actually kind of a great segue. So let's look at another example here. I'm going to get rid of all of this. So before I continue, of the few people that are left in the stream, is there any questions or something you want explained more? Like this, I'm about to move off of composition. Hopefully I've been able to show how it could be used for creating general functions for reusability, and hopefully shown that, you can move stuff around associatively. But is there any other questions or anything like that before we move on to the currying? I'm going to take a sip of coffee. That's a good question, Bob. So we do have other composes that are available. Let me actually do some of this. Oh, you don't need to see what my work life's like. Let's see here. Let's go Crocs, and we'll go to this, and then go to this. Okay, I'm not going to get into these too much, just because, not Crocs, we want functions. Just because there's a lot of explanation that has to go into them. So we also have these other compose functions. This one, compose P and compose K, they are also in Ramda. So if we look at compose K, compose P, when we start talking about ADTs, we'll get into these. So like this compose P is a way to compose promises together. Compose K is a way to compose what are called Kleisli arrows together. So before we start talking about Kleislis, we'll have to introduce functors and some other things as well. We also have in Crocs this compose S, which is a way to compose another data type called semigroupoids. But it's basically the same sort of thing. It just lets you kind of move between categories. Well, not move between categories, but nope, I don't want to start explaining that part yet. We also have another function inside of combinators called compose B. And we'll talk about this. This is the Bluebird compose. We'll talk about this next episode when we talk about combinators. But there are other ways to compose things together. And they're available to you. If you want to read the documentation, check it out. They have it for Ramda. Oh, is there an error? There we go. They have it for Ramda, and we have these in Crocs as well. So good call, good call. And we'll definitely get to those in this series, for sure. Any other questions or anything before we move on to currying? Okay, I take your silence as a resounding no. All right, so let's look at some imperative code here. Now, this is one way to find an average. And again, I know this is contrived. Nobody does this anymore, but who knows? You might have some legacy code that is using something like this, right? But this is a perfect example of just some imperative code. Again, it's contrived. It's just getting a sum, but I bet you will find things like this. The thing we're looking for here is this pattern of creating some sort of state in a function, working on said state in some manner, and then providing some sort of stateful computation or stateful thing back. So let's see what this does. If we put in 50, oh man, you did not do well on these quizzes, Ian. 74, 75, and then maybe we'll do a 65. Oh, you did horrible. So we have this. We can then apply this to AVG and then get an average back. Okay, so I just barely, well, no, I wouldn't call this passing. Passing to me is 80 or above, but hey, whatever. So I did a horrible job on this, and we'll probably have to retake these lessons again. It's just ridiculous. But this is basically what this function is doing. It's taking an average. And do we want to talk about currying? Currying, yes, we do. All right. So I guess before we get into this, let's talk about what currying is. It would be nice to have an example for currying, and I think this will get us a really nice example for currying. So let's kind of just go down this path, and then we'll get into currying and partial application. Because yeah, we are going to need, yes, we will need to actually curry some functions here. Okay. So one of the things we can do here, because what we would want to do is actually break this up. If we were going to throw this into a composition, we're going to want to break this up and into, a couple steps here. So we have two steps going on here. We have, not only do we have this state that's being worked on, which is one of the things that it can let you get away from, but we also have two steps. We're going over the list and we're summing each of the values in there and providing a sum for this. And then from there, we're going to divide the list, or we're going to divide the sum by the length list to get, our average. It's just your simple average to calculate. So we really have two things going on here. So get sum. And then here, we want to calculate result based on that sum. Okay, so let's break this up. And one of the things I guess we can do here is move from this for loop and get rid of this assignment by doing a little, I'm sure if you've read Getify's book, you got to parts about ways to handle getting rid of for loops and things like that. I haven't really read too much of it, but I believe there's a chapter somewhere on that. So one of the ways we can get rid of this is through what's called a reduction or a fold, right? This list actually has what's called a reduce function on it. So instead of doing this, we could just calculate this sum. Instead of doing this let, we can make this a const. So we only calculate this sum once. And then what we'll do is do a reduction on this list. Reduce. So what we want to reduce this to is take this list of numbers and we want to make it into one number. So we want to take this list of numbers and fold it in some way and take every single element into account and get back a sum. So we could do that with a reduction. Super simple, super easy. Now, well, I don't want to say that. I'm sorry. I shouldn't say things like super easy. But it's something we can reason about, right? So it takes two parameters that we really care about. It takes others, but really we're just going to care about these two. Yep. So here on the first function, on this first function, the first thing it takes is a function, and this is what your reduction function is. It's basically how do you want to concat these things in this list. And the first thing that comes is a accumulator, which is something that's going to be passed to every iteration inside of that list. So we want this to actually be our number, right? So what we want to do is take that sum, that's going to be our running sum, and then add x to it, because x is going to be the element that we're actually iterating on at that point. So really, that's the only function that we need to have in there, or the only thing we need to do. Now, we could do add, and if we look at Ramda, well, hold on. We're getting ahead of ourselves. So for here, the next thing that we want to do is provide, or the second parameter that this takes, or the second argument that this takes, is our empty value, or something that we want to start our accumulator off with. So since we're summing up numbers, the good empty value is going to be 0. So when this comes in, it's going to set it to 0, and then it's going to take our first number, which is 45, and add it to 0, which will get us, what we want. If there were no numbers in here, then it would give us back a 0. Okay. Yep, there's that, there's that. Okay, so now this should get us a sum. Sum plus equals. Don't need to do this anymore. So now we replaced all of that for loop and things like that into this real simple reduce function. So using that add function that we created later, we don't really need to reuse that or to use it because Ramda comes with an add function. So instead of doing that, we can do this and it'll basically add the numbers for us, right? So if we had our own function that we had, this would be an example of where we would be able to reuse that function instead of having to write it out. Now here there's no number checking going on or things like that, but we could add that to whatever function we decide to use, right? But again, we don't really need to worry too much about that. We'll deal with stuff like that when we get into sum types, like with ethers and stuff like that. So we can also do a little thing, clean this up here, and go like that. So now we get back our reduction. It does the sum, adds all the numbers up for us. We're good to go. So now we see that we clearly have two things. So our first thing that we want to do is get our sum. Okay, now this is where we're going to start talking about currying. So what if we had a function that we call sum, and all that does is it takes a list of numbers and does this reduce? Well, inside of Crocs, we actually have a point-free function called reduce that will take care of this for us. So what reduce does is it takes that concatenation function first, then it takes some sort of empty value. This is what we want to turn it into. Then it takes a foldable. This M here is some sort of foldable. And then it's going to give us back the reduced result, right? So that's the same thing here. This is our foldable. This is our data. This is that reduction function or the concatenation function here. See how the B comes in first and then it gives you back the A. And then it's going to take an M of A, or in our case, an array of numbers. It's going to pass in our empty or whatever our B is. Then it's going to take that and then give back another one of those B's. See? So it's basically the same thing, except now we have it point free. One of the things to notice in all of these functions, the thing that's on the end is the data that we're working on. In this case, it's going to be a list. So to get this to work, all we need to do is use that reduce function. Do r.add, because that's our reduction function, and put in our 0. Now notice I'm not specifying this here. So if I were to just come over here and do sum, notice how I still get back the 274, which is the sum of this list. See how I get that back? That's because these functions are curried. One of the things I could do is if I were to take this off, I would get back another function. And here I can provide what my empty value is. See? And that's because these functions are curried. So what do I mean by curried? And these functions are a little more than curried. They are I don't know. How would you say? They are really super awesome partial application helpers, I guess. But curry is a lot easier to say. But what a true curried function is a function, and let's make a true curried function here. So we will, instead of using r.add, we'll create our own add here. And this will be a good one to show you. So let's get rid of this and go like that. So a curried function is a function that takes only one argument at a time. So say I have this add, and one of the ways you can write a curried function is like this, a to b, and then give back a plus b, right? So I have here in my hot little hand a function that when I call add and put in 45, I get back another function that's ready to take another number, like 100. And notice, as soon as I apply that 100, when I first do that a, that comes to here. Then I get back this function, which is the b that's going to, and then once I have that b, I have everything I need to actually, how would you say, add these two numbers together. So this is what currying is. Now, the real bummer with this is we can't really use it. If we were to try to use it with our average, hold on. We wouldn't really be able to use it with our average. The same way that we did with r dot, how would you say, r dot ramda, or ramda dot add. And the reason why is they're using a special currying thing that allows you to specify different things. So if I were to take this sum and then take these two numbers, we would get an error, right? Oh, and actually we wouldn't get an error because all it's going to do is keep kicking back this function, basically. All right. Okay, yep. So we're not getting the error there because we're, getting that. And if I were to come here and put 1, we should get 4. Oh, nope, it put the string together. Isn't that something? So this isn't really doing really what we want it to do, right? It's actually taking something, converting it into a string, and then adding those strings together. And this is, just a normal problem with JavaScript. Wow, that was a bad example, but this is really cool. I can show this. I'm going to play with this. That's really neat. Now, the difference between that, so we can actually add this back with the r.add, and we see that we get back our normal 6 that we're expecting. So let's jump here, and we'll just do 78, 94, 60, 62, and get our sum of those scores. And using this r.add, hold on. So using this r.add here, it's actually taking care of the application for us. So it's going to, we can look here and see what it's doing. So if I were to take r.add, I get the same thing whether I do 23 and 100. That'll give me 123. But it also handles this. So what it's going to do is either apply them one at a time, or if it has, certain arguments or things like that, it will do it in, say it has more arguments, it'll do it in a curried fashion as well. So I don't need to apply them at all. And this is what's called partial application. And even though this function is called curry, it's really more about partial application. And where that comes into play is, say I want to make a function called, add 10. And I hate using add, but I mean, you could do this with anything. All we have to do is do .add and 10. And now we have a function that has this first thing partially applied, and it's just waiting for its second function. Or it's waiting for its second argument so it can actually run the function. So if we go to here and we say add 10, and then put in 10, we'll get 20 back. And we could do that for any number, right? So I know doing addition and things like that, that's not very groundbreaking. But with some of the other functions that are out there, you can really put together some really good partially applied flows that just provide context or provide, context for your data. So that's the other thing, like with this reduce function. This is using this, right? This is actually partially applying this because like I showed before, I could put in 1, 2, 3, or I don't know if I showed it. And then down here, if I just look at sum, I get 6. But by doing it this way, I now have a function that's always going to add a list of numbers. So I always have this function now, and it's just a matter of taking this one function, applying the context to it, and then getting ready for the data. And one of the things you'll notice about all of these functions is consider this M here to be the data that we're working on. We'll get into that in future episodes, what this M's talking about. But we consider this to be the data. So if you look at every single one of these, the last attribute is the data or in that case, that's just a single function, right? But it's the actual data comes last. And this is what's called data last, right? Everything here is context to run in that data. And that's a good way to think about this, is your last argument to every function you create. So when you're designing these functions to work with composition, I know it's very counterintuitive because in a lot of, like if you look at Lodash, like a really good example before Lodash, I hate going here to these Microsoft sites, but you'll notice a lot of the stuff for the APIs, or a lot of the stuff for like working with the data. Where's their API, FP guide, documentation? Notice how it takes the data first here. Everything here, and if we look at something, it always takes the actual data first. Let's not be an array. Let's go somewhere else. Let's go to count by. So see how it takes the collection there, or it takes the collection and then a predicate that defaults to something. Like we're used to in a lot of our libraries and things that we've used over the years, we're used to having our data first. And we don't want to do that when we're writing these types of flows. Even Ramda does all that. It always takes whatever the data it's working on as the last parameter. Everything that comes in the front is context that can be applied to create new functions. Okay? So in that, does that make sense about how partial application, I mean, I could go on and on and on about that, but does that make sense about how the data is, or the parameters are ordered? Does anyone have any questions about that? Any questions about being able to apply things in this, like either through partial application or I'm sorry, applying as many arguments as you want or applying them. Oh, and that's the other thing too. Like I can represent this as this and still get the same results. Oh, sorry. See, I got the same results there. No, see, there's a cost occurring. That's a good question. So Bob said, should everything be curry always? And I would say for helpers and things like that, sure. But if you don't need to curry, and this is really great. That's a really great question. So say I have some rando function here. A lot of times what I'll do, because most of the time, like say I'm working in a flow, I'll have all my context available to me. So I'll typically, instead of currying everything, like doing a partial application helper or things like that, because there is a cost to it, right? Like you have to build out a new function based on things. Sometimes it has to run that depending on how you had to curry it. Sometimes it has to like run 3 functions and like, do this crazy fold like in the back end to get it to work. So a lot of times, if I'm not making like a reusable helper or things like that, I'll usually just make a function like this that takes all of my context, but then only curry my data so I can use it in a flow. So while currying everything might be great, it may not always be the most beneficial thing. A lot of times you can get away with just separating into two functions your context and your data. So I know if you've like looked at my code or things like that, you'll see me do this a lot to where I'll actually provide all the partial application and things like that. So for instance, that reduce function, since this is, always like this and it takes the data, what I could do is then do reduce like this, and then do r.add and 0, right? Wait a minute. Now this is a bad example because this is already curried, but just by doing it like this, I mean, see how it's ridiculous? This signature matches that signature. But let's go to Fantasyland and kind of pretend that, we're doing something different with these parameters. This was a bad example. But in this case, I would be able to take in whatever my context is and throw it, into a new function that's ready to take the data, because this is going to return a function that's ready to take the data. That's why I didn't apply the X, although I could have, right? You see how this is the same thing as that? Right there? Does that make sense, Bob? Does that answer your question about if things should be curry always? Okay. So now I just want to talk about, before we go on with this, I want to talk about one of the major differences between Crocs and Ramda. And that has to do with how we handle currying. This is a huge difference, right? So before we get back onto this, let's just comment this out here. And let's comment this out here. I just want to address this. So one of the things you'll notice is if you see this function add, if I were to take this function and curry it with r.curry, what do you think will happen? I'll give you a moment. Do you think it would still behave the same way? Anyone? I mean, it would be really nice if this would work, right? Because we have this curried function, and what we want to do is take this curried function and get this to, yeah. So now, if I were to call add and do it like this with 3, notice I get a function back. And then if I do 4, it does the 7. But we could have done that anyway without having to curry this. But what happens if I do this? Notice it didn't apply this function. So I should get 13 back, right, if I add that 10. So it threw away this argument. Even though I would really personally like it to actually apply this for me, right? So To see what this looks like, this is the main difference, one of the main differences between Crocs and Ramda. Now, if I were to use the Crocs curry, see how I get 7? And I could do it like this. See? So this is one of the major differences between Crocs and Ramda. Now, if you want this to work in Ramda, and we'll see why this can get a little unwieldy. This is kind of a bad example, so that's still going to pass. If I actually want this to work with Ramda, I need to go in and build out what it needs to look like. Right? So one of the things you'll notice, now this will work, and it'll work for doing it normally. But I couldn't take any old function that I had and run the partial application helper over it and have it bring me back something I would want. With Crocs, you'll get that. With Curry or with Ramda, you won't. Right? So this still works, right? Because I was able to put it. Now, I think I was reading somewhere that they do a lot of this having to work on the length of the passed-in function and things like that. I believe it's in there so they could get it a little easier to work with different TypeScript libs or Flow or things like that. I don't know how true that is, and I don't know if that actually helps it. But I think it was some rumblings I was hearing as to one of the reasons, not the main reason. There's some readability things and some other good reasons they have for it. But one of the things with Crocs is it's going to be a very big event would have to happen for us to support TypeScript. Because you have to do a lot of things with the library, we lose a lot of the power that we get just from this curry method, if we were to have to get it to work with Flow and other types. And when you use the curry, like the curry from this reduce, it's actually going to be the Crocs curry. So you'll get that same behavior, things like that. And the other thing is, if another function returns a function, it'll still keep currying down and accepting arguments until it applies things and does not get back another function. So it'll always keep taking arguments, So another thing to note about this before we finish up this example, because we kind of need to know this information for what we're about to do. And actually, does that make sense? The difference between Ramda's curry and Crocs curry? And are there any other questions or something you want to see with that? Nope. We good? All right. Cool. Hey, welcome. I'm sorry, sir, but I don't want to butcher your name. Would it be possible for you to put in a pronunciation of how your name is? Sweet. Sumant? Am I saying that wrong? Okay. All right. So I would like to say hi to you, but I don't want to butcher your name on a welcoming. I could probably... Sumant? Something like that? If I'm saying... Perfect. Welcome, Sumant. I'm sorry. I'm so ignorant with things like that. I should really pay attention to people's names and how they're really pronounced. Okay, so now that we have the currying under our belt and we understand what's going on there, hopefully, stop me please if we say something a little different, or if I say something different. We'll continue to use the r.add. And another side note, I use Crocs a lot, but Crocs really only has functions other than some cases where I found like, evolve and things like that, like how they deal with undefined values and things. I found them to not be very friendly, like working with database libraries like Connects and Bookshelf and things like that. So like I've re-implemented those in Crocs just so they work with undefined values a little differently. But for the most part, all the functions inside of Crocs have to do with dealing with ADTs and different logical flows, things like that. Whereas the other ones, not the other ones, but I don't provide a lot of like utility helpers like length and add or things like this or average or, I don't provide helpers like that because Ramda did a great job of implementing all those. And it's kind of out of scope for, what Crocs really is. And it's just a library to work with ADTs, with the given ADTs that are there. So a lot of times I still use Ramda pretty much every day because I don't want to write all of these like add helpers and get the length and bind and like all of these wonderful, wonderful helpers that they have. So anyway, a lot of people wonder why I still bring in Ramda to things. And that's why, is because they did an amazing job implementing a lot of really cool stuff that I will never have to write again in my life. Thank goodness for Ramda. And that's what I need to say. So now we're at a really, really fun part. Well, I think it's kind of fun. So we have 2 steps here. Now that we understand composition, currying, things like that, what looks like a really simple flow, and there's a couple ways we can approach this flow. What looks like a really good flow, or a really fun flow, or a really easy flow, could get a little weird when we're dealing with, how would you say, compositions. There we go. I blanked for the word. And the thing that makes it complicated, and we'll look at a naive way of handling this, and then we'll look at another way of handling this, both in Ramda and in Crocs. But one of the things is this shared list, right? So part of this calculation here needs the list to actually reduce on it. And this calculation here, which happens in a different spot in our composition, also needs the list. So we have 2 lists going on. Now, if you've seen my ADT things, I think you know where I'm going whenever we have 2 things that work on the same thing. But we're not going to approach that yet. That will be our final solution. But right now, we're just going to look at some, I don't want to say naive, but some ways that we can address this, right? So, and it'll demonstrate partial application. Yeah, r.add, I'm sorry. Add, I should have shown this. I didn't show this. But if we see add takes a number, then it takes another number and gives back a number. Oh, and also a little trick for reading these. If you're curious what something returns for this type signature, the thing on the far right is what it returns. The penultimate is the penultimate. I think that's the second to last. Penultimate. Second to last. Last but one in a series of things. Second to last. Okay. So the penultimate is always going to be the data that it takes, right? So you'll notice even on things that take 2 things like this always, well, that's going to return a function that'll take any. Let's find a binary function here. There's got to be a binary function. What is and? Is and binary? Yeah. No. Of course it's not. Any will take the predicate. Anyway. So for instance, this is going to return an array of B's, but the data that you pass to it is an array of A's. So if you're ever like having a hard time reading these signatures, oh, trim, look at trim. So you see here, this is what's being returned, and the data for the trim function is this string. Now, if we have this, the return of this is a number, and the data that it's actually working on is going to be the penultimate one. So that's how you want to set up your functions, and that's a little trick for reading those. Okay, so that's what add does. All right, so now we have our two different steps. We took our for loop and all that, and we moved it into this reduce. And we also made this other function called reduce. Okay? So now let's make another function here that we'll call divide. All right, so this is basically going to be a function that we're going to need to have this list to actually get the length, but we're also going to need to take the sum in as our data. So let's just write this out. And hopefully you're seeing some problems with this that we're going to have. Remember I say we don't really want to hold on to state too much, things like that. But I think you'll start to see the problem as we kind of get, down the road with this. So what we want to do is take the divide length. And remember, the data that we're working on is not really the list in this case. It's actually the sum. So we're going to get the sum back and want to divide that by the length. So our data is going to be the sum. So here we want to take a list. And what would be a better way of doing this? Let's look. Okay, hold on. There's a better way. So if we look here with divide, this is going to take the number that it divides by second. So really this isn't, since it takes an A to a B, it's basically this is A, this is B. This is the number that's going to be on the bottom. So this doesn't really work out too well for us, but we could do a little something called flip on it, right? So what flip will do is flip this around so that way we take in the number we want to divide by first, and then we take that in. So let's just do a little flip here, and we can use their flip. No reason to use the Crocs flip, but because there's some cool things about the Crocs flip, but we'll talk about that whenever we talk about combinators next week. So here we take, we're going to need to take in our list. And we're going to take in a list of numbers. And then we want to take in a number. And then we want to get back a number. Now, I'm not going to do the obvious if this is a 0 or things like that, because we could take care of that in another fashion or in a different way, right? So here we have our compose. And And actually, I don't think we need to do the compose. All we really need to do we do need to compose because we have to get the length. Okay. So we take in the list of numbers and then we take in the number, but we need to get the list back. So here, let's take our list, and then we'll do a compose. And then we'll do r dot divide. But we need to flip this, so r dot flip. And we could have set this up to where we flip the whole thing around, but we didn't do that. All right, and then here we take some sort of number next. And actually, we need to take in the length. So now let's do r dot length. And that's going to be that. So now this should get us back a function that's ready to take something. So let's have some data here. We'll do const data is equal to, and let's get a list of scores here, 34, 89, 90, and 100 there, right? So if we just do this divide length, and we'll pass in data, we get back another function. So if we pass in sum of data, wait, hold on one moment. So that'll take the length, that'll give that. Sorry. Okay, so now that we didn't have to specify the list itself. Okay, so now we have a composition that's going to actually take the length and then bring that in. So now we need to create a new average function. So this basically will take care of this first part and get it ready to take in the sum. So now let's make a little function here. And we'll say const avg takes in a list. And then is going to return a compose of, what is it? Divide by length, and let's change this. And we need to put in the list here. So this is where the partial application comes in. And notice we are having this function where we take this list and then we specify it by passing it to it. And then we have to do this other little nasty bit where we have to take this function and then apply the list to it. You'll see what I mean in a second. This is kind of, and then I don't really like it because we have to specify this point. And there's no reason really to specify this point. But don't worry, we have a way that we can get around it. So if I come here and do that, then it's just a sum. And here we pass in list. Okay. So for now, let's comment this out. And we see we get back the actual list. So this did this whole average and we put it inside of this one function. And remember that we had the two steps that were going on there. We had this first step where we get our sum. That's this first step here. And then we take the result of that sum and then divide it by this length. So to see what this would look like, you know, like how we got from here to here. Oops. Sorry about that. So how we got from here to here is we took that sum. So all we really need to do and then here we just do divide by len. We should get an error, or not an error, but all right, so divide by len, that does that, which gets a number back. Now, one of the things you'll notice here is because we are not currying this function, that it's not applying properly. So now, just by doing that curry, you'll notice, again, one of the differences between Crocs and Ramda is I can curry this composition and it's just going to work like the way that I would expect it to work because it took care of that for me. So if you want to see where it returns that other function, if we do r.curry, we just get the function back. So again, this is the things that you get when working with, how would you say, Crocs, like using the curry in Crocs versus Ramda. So this is just going to take care of it for us, and it will curry it, and we can use this type here to know like what it's actually doing for us, or the SIGI here. Okay, so now we have that average. It's doing all of that, and it's still a two-step process. But, so you'll notice this is more set up to be the composition. We have this divide by len, which will actually take the bit that's applied to it, or the list, and pass it to it, apply that to it. And then we have this sum. Let's put a SIGI on sum, just so we see what's going on there. And this is going to take a list of number and give us back a number. It basically folds that list of numbers into a number. And then average, of course, AVG, takes a list of numbers. Or, I'm sorry, yeah, list of number. And then that's going to kick back a number. All right, see all the signatures line up? Okay. So that's, and actually let's copy that for this. Okay. So again, the composition for this is set up like this, but you'll notice, GC, one of the things that is kind of a super major bummer about this is we need to specify this list. So before I go on, the thing I was trying to show for this is how you could take complicated flows and actually apply a use partial application to split up state in these functions. So if I need to work on a object coming in or some sort of data coming in, and I have two separate flows to work on it, I can actually use partial application to do that. But the result of that is needing to specify this actual value, right? So are there any questions around that part? Would you like more explanation on how this accomplishes that? Or like maybe another example to demonstrate if this one might be a little confusing? And I'll take a sip of coffee and wait. All right, so we're at 1 hour and 22 minutes. And a little bit of behind the scenes here. You might be wondering why I take the sip of coffee. It's not just because I'm thirsty, but it lets me know. Okay, line 10. Divide by len, takes a number, and then gives back a number. What would you like to know about line 10, Bob? Yep. So Bob put in the thing, divide 2 takes 2 args. And you're 100% correct. So let me step through that, right? So we get our first bit of data that comes in. Yep. Length returns 1. Yep, length returns 1. You're right. So now if we look at this signature, I'll just step you through what's going on here. Notice how we take an array. of number, and then we take a number, and then we get back a number. So because we're currying this, I'll show you what happens here. This number hits. And then this takes that number and gives back the length of it, or the array of number, and gives back the length of it. So in our case, we add 4, sorry. So it's going to take that 4, and it's going to pass it to this flipped divide. So remember, divide right now takes its top and then its bottom. We flip this around to where it takes the bottom first. So now what happens is we get back the other function ready to take this. So whenever we apply this function to it, it passes that length, which then becomes the b here, and then gives back another function. And the function that it gives back is this function. Does that make sense? Yep. And like I was saying before, this will not work with Ramda curry. This only works with Crocs curry, right? This is going to apply everything all wrong. Oh, wait. Maybe not. Why not? Oh. No, why not? That's weird. Oh, because, I'm sorry. So this would not work for this. This will work if that's applied, but if we were to do this, it wouldn't work. And that's because we wouldn't get this partial application, right? Sorry, my bad. So now we get back the function. So the only reason we're doing that curry, it basically lets us turn that function into this function. Okay. Anything else, anyone? Bob said, yep, thanks. That made sense. But another behind the scenes, or like why I take the sip of coffee, is I know how far the lag is on the stream. So, all right. So now let's look at another way of dealing with this, because one of the things that's really, really horrible, and this is, we're about to get super duper advanced. One of the things that's horrible is having to take this list here and here, bringing it in, applying it here, and then having to apply it. The only reason we're bringing this in is because it has to be used by this function. So I'm going to show you the Ramda way of taking care of this, and then I'll show you the Crocs way of fixing this. So what we need to do is have things work in parallel, and both of these things work on the same data. So what we want to do, we have this function, which is divide by length, that wants to take the length of something. And let's go ahead and just get rid of this, and just use the length function. So we're going to get rid of this. And actually, let's just keep that in there, just so we can compare and contrast. So there's a really, really cool function called converge. And I think they have the average. Yep. Oh, so don't look there, because that's kind of what we're going to be doing. They have this converge function, and it looks kind of scary. But what it's basically going to do is it's going to take a way to merge an array of functions, or an array of functions. Then it's going to take an array of functions, and then it's going to run a function over that. And then it's going to give us back another function that will take one value and then put them all together and then run and send the result of this into this function to merge it all together. Oh my goodness, that's a mouthful. And it's really hard to explain unless we look at it. So let's make another average function here. And we're just going to do r.converge. And we need a conversion function here. We need a way to actually converge these and merge them together. So what we're going to do is we'll make r.divide. And it's going to take this list of functions and their values that are inside of them, or the values that result from them, and it's going to pass them top to bottom to this function. So what that means is we then need to pass an array of functions. And remember, the way that it's going to be brought in, we need the top one to be on the top of the divide. So the A, we don't need to flip this function or anything anymore. We want the result of the sum on the top of the division, and we want the length on the bottom of the division. Okay? So here, all we do is pass in sum, and then we pass in length. And we get our result. So now we did not have to specify anything. What it did was, as soon as we got our list, it has the same exact signature, same exact everything. But when we got our list, it took the list, we passed it, and it passed it to here. Then it took that same list at the same time, and it passed it to here. And then from there, it took both of the results of those functions and then sent them to this function and then returned the result. So it basically sent this to the first parameter or the first argument of divide, and it sent the result of this to the second parameter of divide and then returned the result. Does that make sense? Again, I'm going to take another sip of coffee. The thing that I'm trying to show you is how to use using converge to do parallel computations, and whenever you have shared state between the different functions, right? That's what this is. Okay, so Bob's good to go on that. Thank you, Bob. Now, another thing we can do, I'll just show you, that's how you do it. Anyone else, if you got questions or anything? Bob's up to speed. Okay, cool. That was a fun little wait, huh? All right. So now we'll go through and just show you how we would do this with Crocs. So it's going to get a little confusing because we're going to talk about pairs or things like that, but just look at the function name here. So we have something called fan out, which is basically going to do this on line 29. It's going to take a value and it's going to put it inside of a pair, right? But before it puts it into a pair, I'm going to pass two functions to it. It's basically the same functions that we have here, sum and then length. And then we're going to explicitly merge it in. So instead of using one function called converge to do it all, in Crocs, you do it a little different. So we'll make another one here. We'll do AVG is equal to compose. And we're going to do fan out first. And then here, we want to put in, I guess, the same sort of thing. We'll do sum. And then here, we're going to do length. r.length, sorry. And here what we're going to do is put in merge. And merge actually explicitly, well, let's just see what it does without that, right? So if we do average with data, notice we get the pair back. So we get a pair of 313 on the left, which is going to be the thing that's applied. And then on the right, we got back the 4, which is the length of this array. Make sense? So then what we need to do is actually use this merge function. And what merge does is it takes a pair and it applies them to a binary function. It could be bigger than a binary, but at least a binary function. It could be smaller too, because we could just throw away the result. Like if we're, and we'll learn about things like that when we get into combinators next week. But here, we just do the same sort of thing of r.divide. And we get the same result. So it's pretty much the same thing here. The only difference is we set this up because we have, there's a lot of times you want to stay in the pair because it is, so fan out only takes 2 arguments max. Yeah, it only works on 2. It only works on 2 functions, 100%. And you're right, it's good that you noticed that. Now, if I want this to work with another one, I have to do another fan out. I won't get into this too much, and then a merge. But I can take, like this fan out and merge, I can take this flow, pass in a function, and if I need to go out, like say 5 levels deep, if I need to do things in parallel, just with some slight rearrangement, and maybe I'll throw a gist up or something. It's kind of, we'll get to this when we talk about product types for sure. 100% when we talk about product types, we'll show these types of strategies. But there is a pattern that you can use to where you fold out, or you just, how would you say, grow all of your data and then fold it back up, right? It's called an is it an anamorphism? Anamorphic. Think it's an anamorphism. Oh man, I forgot it. But it's basically a way to build out data, and then you do just a normal fold to fold all that built out data into one answer. And we'll get into those patterns and stuff once we get into product types and things like that. But it might be a little out of scope for this. Okay, so this is basically the same exact thing. That works on, this. So we are basically able, by using composition, a couple little tricks here, things like that, we were able to take a normal function or a function like this, like this, and create this for reusable parts that we could then use all over our app. And so, for instance, we didn't have to write this division. This division came from another library. We didn't have to write this length to pull this length. We didn't write down the specific steps of how to do this. Who knows how Ramda's getting this length? Between you and me, they're just checking the length like we're doing here and checking a property. But we don't need to know that. We don't care how they're checking the length. We just know that they have a way of getting the length. And we don't really care about the details so much. So by being able to figure out the steps inside of these imperative flows, we're able to kind of figure out what parts of our application and what parts of our functions could become little programs that we could reuse over and over again. So, I mean, I had some more stuff, like I kind of went overboard with the advantage of using the Crocs way versus Ramda. I don't like to speak in advantages, but each one has a cost. And each one has benefits depending on the context you're in. And so, for instance, a lot of it has to do with the team. It's like what the rest of your flow, like I know a lot of people want to say, well, what's this advantage over another thing? Like what's an advantage of A over B? And that's always been a tricky question, right? Because it could depend on a lot of things. One of the things, one of the differences is how this thing is approached. So if you have a lot of different calculations or things like that, you might want to use the converge. Or if you're working like say I don't want to merge this in, I could just create a fan out and do something else and work on it. So if I have a big flow that's actually using a pair already, because remember, this AVG is actually going to return a pair. So I might actually have other parts of my flow that are working with a pair. So I might want to do the fan out in a pair. I may, and a lot of times when you're working with these algebraic data types and, you know, the different types of containers or data types, I guess I should say, a lot of times you don't want to jump out of that data type or that context or whatever you're running in until the very, very end, because it makes it easier to compose those results with other things. And we'll see that once we start getting into ADTs. So really, there is not really an advantage one over the other. Now, as far as things like curry, that depends on a lot of things. A lot of people, or some people, find that this reads a little better than... Oh, I deleted it already. Yeah, I deleted it already. So if you look back, yeah, and I know that's a wishy-washy answer, Bob. I'm so sorry about that. But you can't really say one's better than the other. They're just different approaches to solve the same problem. And it all really just depends on context. So as you start doing, I mean, I don't know your experience level, but as you start doing this more and more, you'll start to notice when you would want a certain technique over something. It's just something that you can't really teach, because I would have to set up all of these contexts and constraints and build out a big app and talk about each one, or each part of the app, you know. Okay, cool. All right. I mean, that's pretty much all I have. I hope that this kind of helped you understand currying and composition and partial application. This was by no means an exhaustive study. Oh, welcome back. Welcome back. This was by no means an exhaustive study or an exhaustive thing of techniques. This is just basically something, just a way to show separate patterns and kind of build up on something to kind of show like how to identify steps and common imperative flows, things like that. As far as I understand, so Sumant says, as far as I understand, R flips the parameters. Yep, that's 100% correct, but only two of them. It swaps two of the parameters. And next week, we'll be getting into that. Sumant, what time zone are you in, by any curious? I'm going to be changing next week time zones. Well, not time zones, but time. I'll be starting at, I think, around 6 o'clock Great Britain time, things like that. But anyway, next week we'll be talking about combinators. Oh, okay, so I'll be able to catch you if you're on EDT. I'll be able to catch you around lunchtime, but so perfect. Yeah. Okay, so this is where we're at. Hopefully I was able to show you. Oh, EDT. I was thinking EDT being... I'm sorry. Okay, so that's Eastern. Huh. Yeah, yeah, totally. Oh, that was from Bob. Sorry. Yeah, I have. I noticed that a lot of people. There was a lot of interest in the state thing that I have up there. So the interest has started dwindling a bit, and I planned as soon as interest started dwindling that I would throw up a follow up. So I have one bit that I'm still kind of working out that's going to be using the state monad for building React applications. Basically, I'm going to take all of the stuff that we did in practical to-dos and distill it down to an egghead thing and only show like the key points. It'll be a lot easier to follow than my ridiculous rambling. That is a new course coming up that I'm putting a proposal in for. And then I have 3 more lessons that I'm going to add to the other one. So that would be to the state one that I have now. So I'm going to add like how to generate random numbers, using it as a finite state machine, and goodness gracious, one other one. So yeah, I will be having those coming up soon. And then I have kind of just a taste. Let's see here. Let's see if I can do this. Code, no. Documents. Yeah, downloads. So check this out. This is kind of an example of like the series that I'm doing voiceover for. These are all the transitions. So we'll be kind of doing this, and I start explaining set theory and like what you would expect to see in the math, and then immediately show like what this looks like inside of how would you say? This is what it looks like inside of JavaScript. So we're able to take all of this stuff, this simple set theory bits, and actually put it together. Come on now. Put it together, explain the theory behind it, and then immediately show examples in JavaScript of how this theory goes. So Bob had some feedback. Just a feedback on the state course. It would be cool to start with why you would use it. The maybe course is quite clear on the benefit. Oh yeah, I didn't write the many course or the maybe course. That was Andrew. Oh my gosh, I forgot his name already. But yeah, you're right. So I didn't want it to be like why you would use it. It was mostly just the API, right? I wanted to get away from like why and when. But, you know, I'll take that to heart and definitely approach that in my further lessons. So that's awesome. Thank you so much for the feedback. I'm always open for feedback. But anyway, so this is some of the stuff I have coming up. I'm doing the voiceover and the things for this right now. This will be on the YouTube channel. And this is more about the mathematics behind it, building up to category theory. So, yeah, that's all I got right now. I think I'm going to go have me some dinner. And yeah, thank you so much for joining me. And I will speak at you. Oh, it's kind of hard to duck out of here when your thing's not there. And I'll speak at you later.